So I think I might have time to cover a really neat quantum protocol called Weidmann bomb detection, yeah. Okay, and here we're actually going to have to draw beam splitters and quantum optical tables. So the basic idea is you have a bomb. And you have a whole bunch of these bombs, and you'd like to test them whether they are actually defective or not. So the bomb has a little fuse on it, and the fuse is so sensitive, if you shine one photon on it, it explodes. One photon on fuse, bomb explodes. So of course you keep these bombs in the dark. And what you would like to do is you would like to see, and some bombs are missing fuses. Some bombs are missing fuses. So you would like to make sure these bombs actually have fuses. But you want to check to see whether they have fuses without exploding them. But of course, if you look at the fuse, it explodes. So what do? Well, I am going to what we're going to do is we're going to set up two half-silvered mirrors and a source of photons. And this is a plane mirror, and this is a plane mirror. So this is an interferometer. And we adjust it, just interferometer, so that if there's nothing in the path, nothing in path, everything goes to this detector. 1, detector 2. All photons go to detector 1. So, I mean, you can model this as basically this is a Hadamard date, and this is another Hadamard date. And when you multiply them, everything goes to this detector. And now, what we're going to do is we're going to put a bomb here with this fuse over the path. Well, assuming it has a fuse, the fuse will be over the path of this photon. No bomb, 100% detector 1. Suppose there is a bomb. Well, what happens is a photon goes through. With 50% probability, it goes this way and explodes the bomb. %50 probability, bomb explodes. In which case, we actually don't see any signals at the detectors. If the other 50%, it goes this way, and it goes up this way, but now there's no interfering ray coming from this path. So the photon goes this way with 50% probability, and this way with 50% probability. 25% detector 1, 25% detector 2. So if the bomb is defective, detector 1 is the one that's triggered. If the bomb has a fuse, 25% of the time, detector 2 is triggered. So whenever we get detector 2, we know it's a good bomb, and we know that there's a fuse in it, and we have not looked at the fuse. So of course, this is something you cannot do classically. If you have a bomb that has a fuse on it, and you want to check whether there's a fuse, you have to look at the fuse somehow, and if you look at the fuse, the bomb explodes. So this is a way of getting some bombs out, or some bombs which we know have fuses out without exploding them all. And if you want, you can set up a much more complicated optical experiment which explodes the bomb not with 50% probability, but with maybe 1% probability or 0.01% probability. So you can set up a much more complicated optical experiment which almost always detects good bombs. But that's more complicated, and I'm not going to go through it in this class. Okay, good. Yeah?
Can you make a device which has sort of an arbitrarily small, as in you can make this interferometer as complicated as you want, and you can get whatever probability of bomb exploding if you want, basically?
That's right, but you can't set it all the way to 0. There has to be some probability the bomb explodes, but, well, basically the idea is that you have mirrors so that the photon goes up and down here many, many times. And the more times it goes up and down, the lower probability you can get it of having an actual bomb explode. But I guess to get 0, you would have to have it go up and down infinitely many times, and that doesn't work. So that's the basic idea for reducing this probability. Any other questions?